All right, so today we're going to be looking at solving systems of equations. Well, this means that we're going to be finding the intersection points. So for example, I have these two linear equations. These are lines in slope-intercept form. And so if I look at a graph of them, okay, if I look at a graph of them, they're going to cross paths at some point. And that point is the intersection point. So instead of graphing this, though, I can see that y equals y. I mean, that just makes sense, right? So where are they going to have the same y value? Well, that's where they're going to have the same x value as well. So I can set these two pieces together. So if y equals y, then that means that negative 4x plus 10 is going to equal x minus 10. Now I just need to solve. So I add 4x to both sides. And I can add 10 to both sides. So the 4x's over here cancel, the 10's cancel. So I get that 5x is equal to 20, or x is equal to 4. Knowing that x is equal to 4, I can plug this back into either one of these equations. Why not the second one? So that means that y is equal to x, which we just found is 4, minus 10, so y is equal to negative 6. So this has an intersection point of 4, negative 6. Now these are two equations, but we call this a system of linear equations. A system means more than one, and so here we have these two equations. So if we want to find the solution, the common x and y value, it's where they have an intersection point, which is at 4, negative 6. Now, I don't always have to do this, and I didn't graph this, even though I could have, because these are both in slope-intercept form. Sometimes they're not in slope-intercept form, but these are still equations, linear equations. Rather than solving these for y and graphing them and going through that process, I can solve using two methods. The first is called substitution. And this is where I solve for one of the variables and plug it back in. So in this first example, we can see that I have two x's and two y's between these two equations. Now, if I'm going to solve for any of these, I need to isolate it. However, you can see that this x and these two y's have coefficients that if I divide out, will leave me with fractions. So because this x value here has a coefficient of 1, I'm going to solve for that. And I can solve for that by adding 7y to both sides. And so now I'm left with x is equal to 7y minus 4, just by sliding the 7y over to the other side. If I take this x and I substitute it in to the top equation, which was 7x minus 5y is equal to 16. And notice I left the x blank because I'm going to take what this value of x is and plug it into substitute in for x. So this is going to be 7y minus 4. Now I only have y, so I can distribute this 7 in. So I'm going to have 49y minus 28 minus 5y is equal to 16. So combining my y's, 49y minus 5y is 44y minus 28 is equal to 16. I can add 28 to both sides. So I get 44y is equal to 44. If I divide 44 on both sides, I get y is equal to 1. Now, since I already have this equation solved for x, I can plug this y into there. So that means that x is equal to 7 times y, which in this case is 1, minus 4. So x is 7 minus 4, which is 3. So the point, I always write it as a coordinate pair, x comma y. So that's 3 comma 1. That's my solution. For number 2, I have the option here. I mean, I really could solve for x or y in the second equation, but again, it will give me a fraction, which I don't want to work with fractions. So here, I can solve for x or for y. So I solve for x in the first equation, so why don't I solve for y here? And I can do that by subtracting x on both sides. So I get that y is equal to 7 minus x. So when I plug in the y, or substitute it into the second equation, which is 5x minus 6 times y, is equal to negative 20. Again, note, I replace the y, I leave it blank, and I substitute in 7 minus x. So I get 5x minus 6 times 7 is 42, minus 6 times minus x is plus 6x, is equal to negative 20. If I combine my like terms, I get 11x. If I add 42 to both sides, I get negative 20 plus 42, which is 22. And I can divide both sides by 11 to get 1x is equal to 2. Again, I can take this x and substitute it in, plug it into that equation I solved for here, and say that y is equal to 7 minus x, which in this case is 2. So y is equal to 5. So my answer is x comma y, or 2 comma 5. Substitution is nice. However, I hope that you can see that if I had coefficients here, so let's say this were 3 and, 7, no matter what I would solve for here, I would have a fraction. And I know many people do not like working with fractions. And personally, I'm comfortable with fractions. Hopefully I should be. I'm a math teacher. But I still prefer working with integers. So in this case, I'm going to use substitution. But if I didn't have a nice coefficient or something that would leave me with no fractions, I would not use the substitution method. So there's another method, which is called the elimination method. And this is where we basically change the value of one equation. Now here, these two examples, substitution could work for either of them, but I'm just going to show you elimination in these cases anyway. So here, the point of elimination is to eliminate one of the variables. And we do that by multiplying. So here, if I look at these x values and these y values, I can see that they're multiple. So if I multiply this 2x, or this x by 2, I'm going to get a 2x here. So why don't I do that? I'm going to multiply this whole top equation by 2. And so I get negative 2x minus 2y is equal to negative 2. This bottom equation is still 2x plus 5y is equal to 12. Well, what if I added these two equations together? Negative 2x plus 2x is 0. Negative 2y plus 5y is 3y. And negative 2 plus 12 is 10. So here I get that y is equal to 10/3. Here, because y is equal to 10/3 is a solution, it's unavoidable. Oh, actually, this is not a negative 2. I made a mistake. So I'm just multiplying this by a positive 2. So negative 2x, that should be a plus 2y, is equal to a positive 2. Oops, did not want that line. And the second equation is still 2x plus 5y is equal to 12. So now, again, I'm going to add these equations. Negative 2x plus 2x is still 0, but 2y plus 5y is 7y, and 2 plus 12 is 14. So y is equal to 2. Hooray, no fraction this time. Now, once I get this y is equal to 2, I have to use substitution, but that's fine. So I'm going to plug this into either of these equations. Doesn't matter which one. So I'll use the second equation. So I'm going to get 2x plus 5 times y, which we know is 2, is equal to 12. So I get that 2x plus 10 is equal to 12. So 2x, if I subtract 10 from both sides, I get that 2x is equal to 2. So x is equal to 1. So my solution is 1, 2. For the second one over here, again, I want to eliminate. So here, it's probably going to be easier to multiply by 2. So I'm going to multiply actually by a negative 2. And so when I multiply this by negative 2, I get positive 2x plus 14y is equal to negative 36. Did not want that line there. And I'm still going to carry over the same equation on the bottom. So I get negative 2x minus 9y is equal to 26. And again, I'm going to add these together. I have another 2x and negative 2x, which is 0. 14y minus 9y gives me 5y. And negative 36 plus 26 is negative 10. So y is equal to negative 2. If I take this y, I'm going to substitute it in. Again, I can use the second equation. So negative 2x minus 9 times y, which in this case is negative 2, is equal to 26. So negative 2x plus 18 is equal to 26. So negative 2x, if I can subtract 18 from both sides, I get that this is equal to 8. And so if I divide both sides by negative 2, I get that x is equal to negative 4. So my solution is negative 4, negative 2. So if we have a system of equations, we can solve using elimination or substitution. And actually this first example that we started the lesson with, that was an example of substitution. I recommend you use a graph to check your answer, and also to plug these values back into both equations to make sure that they equal what they say they equal.